Hello. In this video I'm going to explain the Project 3 report for shortest path routing for computer networks. My name is Adhel-Jose Rivera-Rodriguez and my professor is KG Lu. Here we have the table of contents of the report, and we'll have the introduction and some of the basics of shortest path routing problem, which for these types of problems we have a graph data structure, which is a graph of non-linear data structure that consists of a collection of nodes and paths, which, for example, this is the problem stated in the in the project. Each of the states, let's call it that way, it's a Washington, California 1, California 2, each of these are nodes with each line which have being a path. To take said path, you have to each path has a certain cost, which is the number that is tied to the to the path. A network, the way we can represent a network using this graphs like this is that we can use each node being a router and each path being the distance from the from the node to that node, which might be which could be considered as the distance or what it costs. Excuse me. Or what it costs to take that path, as in, for example, if it's very long, the path, it will require a much more powerful signal to send it, which could mean that there will be a higher energy cost, which is why that path is not taking much and costs that much, because it has a higher cost of taking that path. The shortest path routing problem, and I'm going to bring the graph again here, is what is the shortest path given this graph to, let's say, based from this problem right here, to what is the shortest path from New York to California 2? Because let's say we can take dozens of paths. We can just go to Minnesota, then go to Utah, then go to Colorado, then go to Texas, then go to California 2, which that's a path. We can also take New York, Pennsylvania, and Illinois, then Nevada, then Colorado, then Utah, then California 1, then to California 2. Those are all valid paths, but each of them costs differently, and we want to know what is the shortest path that can be taken. Which from here we can see that the one with the shortest, well, not see, but the shortest path is the New York, DC, Texas, and California 2. That is the shortest path with the least amount of cost and least amount of hops, which is how many routers or states we have to jump to send said data over there. To formulate the shortest path routing problem, we have to set up a couple different variables. First, we need the nodes and edges, which is to create the graph like the one that I just showed you. We also must need the starting node, which is where the algorithm will start searching, and the destination node, which is where the algorithm will terminate and return the path to the starting node. Which, for example, once we arrive at the node we want, at the state, we do not have to continue searching. We can just terminate right there, and we already know the shortest path because it was the first one that it was reached. Of course, the algorithm is implemented differently because it's not that we take random paths. We actually take the path with the least cost to get there. The algorithm must also be able to know which nodes have already been visited to make sure that the algorithm does not enter an infinite loop. For this, a visited array or set is required. which is valid, the algorithm must also know in which it is currently on, so a current node variable is needed as well. The algorithm must also have an array that can store the current optimal path to the current node. This way, when the algorithm finishes, the path can be determined by going backward on the current best path array. The way this works, for example, let's go back to the graph. Let's say we have that shortest path, the New York, DC, Texas, and California. The algorithm will first start here, will first the Minnesota, Pennsylvania, and DC first, check which is the cheapest, the least costliest one, and then just takes that path. Here we have the conflict because there are two 300 of cost from the path, but no matter for this example. Then we take DC, then we have two points, because as New York has already been visited, we know that we cannot just turn back and search New York. We have to check New Jersey and then Texas. Then let's say, for example, they take the one with the least path, with this New Jersey. Then from here we can actually jump to Pennsylvania, which is then continue searching. But let's just say we take the shortest path, which is this one, and this one. When we get here, the algorithm terminates, but we have this as the current node. As we have an array that stores the last node we visited, or the best current path. We just go backwards, which is what one did we visit before arriving here in California too? Oh, we visited Texas. Then before we visited DC, and then before that we visited New York. That's the way this works. We have, of course, the constraints, which is the number of which are a lot of different versions, but we only take into I only took into consideration the ones that are actually present in the problem, which is the number of hops, which is not directly considered, but it can because it's the shortest path. Then we have the cost constraint, which is the path with the least amount of cost to take, which, for example, can be done. Well, of course, it takes a lot more. That takes a lot more calculation, I think, and the algorithm I implement does not take into consideration the cost constraints. Here, in this section of the report, I explain some of the most commonly known shortest path algorithm, which is the Dijkstra algorithm, the Floyd-Warshall algorithm, the Bellman-Ford algorithm, the A-star algorithm, which are all algorithms that take the shortest path to the destination, each implemented differently, and some have some have more benefits than others. For example, the Dijkstra algorithm cannot handle negative weight algorithms because it will enter an infinite loop, because it thinks that, oh, this path is the least costliest path, so I'm going to take that one. But then when we come around again, it will probably just go down that path again, and it leads to an infinite loop there because it continues decreasing. Other algorithms like the Floyd-Warshall and the Bellman-Ford fix that problem, but are more complex in that sense. We also have the A-star algorithm, which was not considered at first as a pathfinding, as a shortest path routing algorithm, but was later considered to be one of the best because of its efficiency and all that. Then continue along. For this part, I decided to implement the Dijkstra algorithm because there are no negative path values, which means that any shortest path algorithm can work. And it's also the simplest to implement, because if there are no negative edges, its performance will not be affected, and the graph is static, which is another constraint, because other algorithms can handle changing graphs, like, for example, a map, GPS network map for Google Maps or Waze. The Dijkstra cannot handle that because if a path changes when it tries to go back to say, hey, this is the path I took, that the edge that it took, it can disappear and then it just crashes the algorithm. Other algorithms can handle it better because go because of the other ways that it handles it. But considering that the problem does not have to do with changing graph and it does not have negative values, I did chose the Dijkstra algorithm because it works for it. Now onto the coding part. I'm going to bring the pseudocode here. Here I have the the pseudocode designed for the algorithm. We have to first initialize as the Dijkstra algorithm implements. We have to set all the nodes to infinite value, and the previous node there, as in the start there are no previous node, we have to set it to null or undefined or something like that because it does not exist. Which is this part right here, which we set all the different nodes to all the distances to that node to infinity, and we set the previous node as undefined because we have not visited, which means there is no previous node. Then we add each vertex to the queue to the unvisited queue to make sure that to count all the nodes that we have not visited, and as the algorithm has an array that checks which node has been visited, we have to add all the nodes to that array first. We also set the distance to itself as 0. Then, to make sure all vertices are processed, we have we check the queue and continue looping until we have visited all the paths. It checks which is the least distance and moves to that one, and then sets that node as visited, so it removes it from the unvisited queue. If that node equals the destination, then the whole algorithm stops, and not the whole algorithm, but the searching part of the algorithm stops and continues to the printing. If that is not the destination, it will check the neighboring vertices and check which of them is the shortest. If there is a shorter path, it will then go through that path, through that node to the next graph. Down here, we check the we check which is the destination, which means we have arrived at the destination, and then it goes from the destination backwards to print all the path, to print out all the path. The pseudocode I implemented using a set, but I changed it to printing it out in a string, which is better. Here. The best case complexity of the Dijkstra algorithm is O of b plus e times logarithm of b, where b is the number of vertices of the graph or paths, and e being the number of edges on the graphs or nodes because of nodes. Now I'm going to go over to the algorithm and explain it here. First we import a matplotlib pyplot to make sure to represent the graph. Here we have the programmed representation of this graph. I'm going to put it here. This section of the code here is a representation of this graph, where each node, let's say for example we have the Washington node, to California 1, it has a weight of 1050, which is right here. Then from Washington we can actually go to California 2, which has a cost of 1,500. And from Washington to Illinois, we can also take that path with a cost of 2,400. All of this, we go through all of the different nodes, and we also have to. This graph can actually be directed, where there is no way to turn, where you cannot travel the same path you took, or traveling back has a lower cost. That is the way the graph is implemented. But we can set it that it costs the same. For example, here we have the Washington. To travel to California 1 is 1050. Then to California 1 back to Washington is actually 1050. That's not the number, but you get the idea. Here we have that's part of the code that was no longer used. Here we have the main function of the Dijkstra algorithm. We give it the network, which is this section of the code. Here is where it's declared. The starting position, which is where we're going to start, and what is the destination node. We then start up a path, which is the best current path. We define an array of the adjacent nodes and a queue for all the non-visited nodes. Then we set for each path the node is we set for each node that is not the star, for each node the value of infinity. Then for each adjacent node we set that it does not have that path, that there's no path we have taken there, and we add it to the unvisited node. Then we set here the value that the path at the start, the path where we start is value 0. Then we continue checking each queue, go and check out all the different values of the queue. We have all of this. Then we go down after all of this is removed, after all paths have been checked. Sorry, I rambled on there for a minute. Then after all paths have been checked, we start printing out the destination, the path we took, which is where I was explaining earlier. We print out first what is the destination, which, let's say for example here was California 2, and then we start going backwards where now destination is the previous node which we took. Which, let's say for example, have the New York, DC, Texas path. Well, before the node we visited before California, it's Texas, so we go to that, and then we check if the next node is none, or this is the starting node. As this is not the start node, we continue and print out the destination, and we print out that node and continue until we have arrived at New York, which before New York there is none, which is the reason why we set each node to have the null previous pointer. And then we break the algorithm, and we have finished the algorithm. Here we have the 3 shortest paths required here, and starting, we can see we have the shortest path to New York from California is starting from this position where this is where the packet is sent. We have New York, DC, Texas, and California. That is actually the best shortest path from New York to California. Then we have from Washington to GA. Washington to GA, we have Washington. Then we go to Illinois, then we go to Pennsylvania, PA, and to GA. Then from California 1 to New Jersey, we go from California 1 to Utah to Minnesota, and then New Jersey. And we can actually just create another path, which is just calling the algorithm, giving it the network, which is the graph we created up here, and which is the representation of this. And then let's say we want to know the shortest path from GA to let's say Washington, to prove that the algorithm can work both ways. As we can see, we have the shortest path from Washington to GA, just Washington, IL, PA, and GA, and the reverse is GA, PA, IL, and WA, which is the reverse of the path. But let's just do another example. They have from GA, let's go to UT, which of course I think the shortest way. The algorithm has two choices. We can actually go either up here or go down here. Let's see which one is the shortest path. Goes to GA, then goes to NE, CO, and UT. Sorry. And here are all the references that were used, which can be accessed in the document. Oops, this is not supposed to go there. Sorry. This is the references. And well, this is all from my part. Adhel-Jose Rivera out.